Now we're going to get into some of the more technical detail of programming. So you should have started the assignment questions by now and maybe done a few of them. That's quite good. We're going to have a look specifically at the use of macros, and you'll have seen these in the code. Let's just have a look at a piece of code to see what we've got. And for this piece of code, I'm looking at the at question 25, which is to do with the traffic lights, or the pedestrian crossing lights to be specific. And you'll see these macros. So what we do in a macro is we define a really useful name for something which is quite difficult to understand and interpret. So for instance, port D, ORD equals 1, shift left PD3, this sort of thing here. We're going to look at this in detail, but really what it means is it means turn on the red LED. We can turn off the red LED, and of course different LEDs are connected to different pins, so therefore we can turn them on and off, and you can see how each one is labelled. And then of course we want to test to see whether the switch, the pedestrian switch, is pressed or not. So this push button switch 1 over here, when it's pressed, it will go to 0. That means it's an active low system. And when it's released, it'll be high. So active low means that when you press the switch, it goes low. Now, we can test to see if a switch is low, we can test to see if a switch is high, and these are macros that we can use in our program. So as you go down in the program, you'll see that in our main loop, which is our automaton, so that this repeats forever, whatever's inside this while loop will repeat forever, and basically all it does is it tests to see if the switch is pressed or not, and then it turns on a sequence of LEDs with some delays in between. So that's the general idea, but then how do these commands work? Set orange LED, check to see if a switch is pressed or not. And we're going to go into those in quite some detail, and you need to understand this in detail. And this is where it gets quite heavy fairly quickly in the course. So let's have a look at these macros and the use of the term bit masking, which means that we want to test or set a specific bit within a register or a memory location. It doesn't have to be a register, it could be in a variable. We could test or set or clear a bit in a variable as well as a register. And we do this through bit masking. In other words, identifying the specific bit we want to check or set, and then only setting or testing that particular one. And so we make use of our Boolean identities, and we use the OR function. If we OR something with 1, then we are forcing it to take on the value of 1. If we OR it with 0, then we are meaning it will keep its existing value, x don't care or existing value. If we AND something with 0, then we are forcing it low, and if we AND something with 1, then we are keeping it at its existing value, so don't care or existing value. Now we're going to make use of this. Say for instance, I've got port B here of my microcontroller, which is connected to some LEDs, and I want to turn on a particular LED. We want to force a bit. A single bit, for instance, the red LED in this case is connected to, well, it's connected to D.6. And I'm in this example using B2, when B2 is connected to the green LED here. We only want to force that bit high, we want to keep the other bits as they are. And so you can see the clue here is if we want to force a bit high, then we need to OR it with 1. But if we OR the other bits in the register with 0, then they will maintain their existing value. If we want to turn off an LED, that means clearing it to a 0, then we set that particular bit to 0, and the other bits we keep as they are. So we AND it with something which only has a 0 in one specific bit location. And that's what these commands mean. We're going to unpack them in a bit of detail. So here's the macros for defining the green LED and defining the clear of the green LED, setting it and clearing it. And we use macros because it makes our code easier to understand. Imagine in your code, let's go back to this code, at some particular point you want to change an LED from one pin, say it's on B5, which is this orange LED is on B5, and you want to make it B4, then all you have to do is change it in one place in the code. You don't have to look through the code to see where you've used port B.4 and change it everywhere in your code. You only have to change it once, and this makes your code transparent, readable, maintainable. So that's what you're looking for, and that's why we use macros. So let's have a look at the anatomy of an output macro. So what happens is this command, let's just unpack this command. Set red LED is, well, we know the red LED is on port D, pin 3. So what does this command here mean? Well, when we unpack this, this is just a simple contraction for this. That's a common C contraction. We do it with multiplication, subtraction, division, and of course we can do it with shifting, and we can do it with testing of via bitwise testing of ands and ors. In this case, this is an or command. So what we're doing is we're just slowly unpacking what all of this means. What does this mean? Well, actually, PD3 is just a macro itself for the number 3. I could have just used 3 there, but PD3 is quite clear to me that I want port D pin 3. Now, what does 1 shift left 3 means? Well, it means if you've got a 1 in this position, which is what you've got initially with 1, then you move it 3 places, 1, 2, 3, and this becomes the number. So now we're going to OR port D with its existing value and this number here. So remember, ORing it means, if we go back to our macros, if we OR something with a 1, then it goes high. If we OR it with a 0, that means it keeps its existing value. So what we're doing here is we are reading port D, we're ORing it with this combination of bits, and that means that all these other bits, no matter what they are, those 4 there and those 3 there, if we OR them with 0, they maintain their existing value. And if we OR this with 1, it means it will force it high. So the output of this will be exactly the same as the input, except one bit will be forced high. And if you look at this, you can see this taking place with a simple using OR here. We're taking this particular bit. It doesn't matter what these bits are. I've just arbitrarily set them at some value. If we OR them with 0, they maintain their existing values. But of course, if we OR something with a 1, then what we're doing is forcing it to go high. Let's have a look at the equivalent, which is to clear the red LED. So when we want to clear the red LED, we want to force a bit to 0. Of course, looking at our Boolean identities, the way we force something to 0 is we AND it with a 0. So we're going to AND the specific bit with 0, and the other bits we're going to AND with 1 to make sure that they keep their existing values. So we're going to unpack this one in exactly the same way. Again, this contraction is just expanded into this. And what we have to do is we want to force a bit to 0 means we have to AND it with 0. So what we do is we take our number, which is, again, we're just unpacking this. I've got this line repeated here. Let's take that out. And I've taken this number here, and what I want to do is I want to AND I want this bit to be 0 and the other bits to be 1, so that's why we invert them, and we end up with this. So if I AND something with 1, it maintains its value. If I AND it with 0, it forces it to low, and that's what you can see happening here. Here's our arbitrary bits in the register which are already existing and we want to maintain, and we AND those with our bitwise AND with a single 1, and then we end up maintaining those values. Of course, this one we want to AND with a 0 to force it to go low. So I want to make it doubly clear here, just something. This is the bitwise AND. It is not this, which is the logical AND, okay? for doing ANDing of logic to see whether a variable has got a true or false value. Okay, so we're doing it bitwise, bit by bit. Now we've also got this, the if the pedestrian switch is low. So this is in the assignment, and it'll tell you which one of these you're going to do, and it'll give you the specific registers. But I just want to go over this understanding, because we're not actually setting. What we are doing is testing a bit in this position. We're looking to see which bit is set or cleared. In this case, we're looking to see if it's low. Now let's just double check that we know what's going on. Remember, our switch is active low. So you can think of it as a voltage divider, which is exactly what it is, with a pull-up resistor, and it has a switch to 0. So what happens is, and I'll go into this a bit more detail shortly, is that when we press this, it goes low. So we want to know that the switch is low. Let's have a look at that. So if the switch is low, because we're active low, so what that means is that if whatever is inside this bracket is true, do whatever is inside the braces. So you've got to remember that. We're not talking about high or low, we're talking about, is this true? And what does true mean in terms of C programming? It means not 0. So if this is a number in here which is not 0, then it is true. So you've got to actually now think about PED switch is low. If this switch is low, let's have a look at the actual macro and see what the macro says. The macro, here's the macro for the low. So you've got to unpack this to find out whether this is true or not. So you've got to know your bitwise logic, and you've got to test the specific bit you want to test, and then you've got to see whether the result is true or false. And so if it's false, that means that the result of this logical testing here is 0, and if it's not 0 and it's some number other than 0, it could be 1, could be 0, 1, 0, or it could be something else, then what you've got is something which is true. So what we're looking for is something which is true here. So you've got to think about this and unpack it for yourself, and this is an assignment question for you to do. Now, I want to delve even deeper into what's going on here, and I want to have a look at the actual, well, it's not really the actual circuit, but it is the a representation of the circuit that is inside your microcontroller. Now, thinking back about what you've done already in terms of digital logic prior to this part of the course, you've got something called RTL, Register Transfer Level. And what you have in RTL is you have a small control unit which is highly complex, a very actually complex finite state machine, and you've got a data path. And so what we're looking at here is we're looking at part of the data path. We're not looking at the control unit. We can see here some signals, control signals coming from the data path, like WDX, RDX, and so these are control signals from the control unit, and the rest of this is the data path. So let's just have a look at the microcontroller. In the data sheet here, this is a block diagram of the AVR. There are several block diagrams around, but what it's showing you is mostly here what is shown is the data path, the bus, the registers, the memory, and the arithmetic logic unit, which is where the addition and subtraction takes place. And you've got the status and control registers, but then you've got this simple thing called an instruction decoder, which has a whole lot of control lines coming out of it. And really this is the control part of your RTL system. So it's a very small part. If we looked inside a microcontroller, for instance, let's go to Zepto bars, and we'll look for an AVR, and we'll look inside there's an Atmel8. So this is looking inside the plastic of the microcontroller to see the electronic circuit itself. So what have we got? We've got a whole lot of regular pieces, a lot of lines, where the control unit is and how big it is. Maybe this is the control unit, maybe this is not it, maybe it's this bit up here. But a lot of this is really the data path, and a portion of it will be the control unit. Not a huge portion of it, but a significant portion of it, and it will be fairly complex. Interesting, if you ever get into the design of something like this, it'd be fascinating to know exactly what's going on. So let's have a look at what happens actually inside one of the pins of the microcontroller. And there are, we've got port B, port C and port D in this particular microcontroller. Other microcontrollers go up to, well, there's Atmels that have A, B, C, D, E, F and G ports on them. But each port has a number of registers. And there are 3 registers in an AVR. There's the port register. Now I want to draw your attention to the fact that this is in capitals. So when I say the word port, I'm thinking about the 8 pins on the microcontroller. But when I say port register, I'm thinking about a specific 8-bit register, or I'm thinking about a specific bit within the 8-bit register. And that's why in this documentation you will see, and in the datasheet you will see this as capitalization. Port, you'll see pin as another register which is capitalized, and DDR, which is data direction register. And these are actual registers. But when I talk about the word port, I'll be quite specific about whether I'm saying it is the port register I'm talking about, or whether it is the port in its entirety, which is all 8 I/O pins together. So here we have a register, which is the DDR. Here we have, it's not in capitalization, but this is the port register here. And then we have the pin register here. So now we've got our 3 bits, and these are only single bits of the register. We're only looking at one I/O pin of the microcontroller. We have multiple I/O pins. Each one of them will have its own copy of this. Now let's have a think about these registers and how they work. When the microcontroller is powered up, the data direction register, the port register and the pin register are all cleared to 0. So the Q's on each become 0, the outputs of each. And that means that the data direction register has a 0 output, which means that this pin in its entirety is configured to be an input. So that's how I've shown it here. I've connected a resistor, a pull-up resistor, to VCC and a switch to ground. And you can see at the moment that the 5 volts, potential 5 volts being VCC in this case, is high. And so we've got a high value on all this logic through here at the moment. This tri-state buffer, I've described a tri-state buffer up here because you probably won't have come across one, but it's like a tap. When it's 0, the input does not get to the output. And that does not mean that it drives the output high or low, it just means that it's disconnected. There is no drive. If this is high, this is unconnected. If this is low, this is unconnected. The only time the input will be connected to the output is when this goes to 1, and I've shown that with this truth table up here. So at the moment what we've got is everything is high because of this pull-up resistor. All this potential is high, and this signal here is 1. What we're waiting for is for the control logic to put a 1 on here to actually read that value into the data bus and take it away to do something with it. Of course, if I close this switch, what happens is that this point here goes low, this goes low. Let's just grab this. This goes low, and we'll just highlight these as low all the way through. And a 0 will go through to our microcontroller. There we go, better choose that one there as well. Okay, so when we pull this, this is all low, and a 0 will go through to say that the that the pin is in a low state, and that will then be fed onto the data bus. So that's how it works as an input. Let's go down and have a look at how it works when it is set up as an output. Well, the first thing we have to do when we want to configure a pin as an output is we want this to be 1. And so that means that this is turned on. So whatever we drive, whether we drive a 1 or a 0 here, it will end up going through this and onto this resistor and LED or some other component that we've got connected. Of course, at the same time, this voltage level, whether it's 1 or 0, will be fed back through the pin. And so you can actually read the state of an output pin by reading the value of the pin register. So it's an interesting way of actually storing. If you've got an unused bit here, you can configure it as an output and use it as a simple little flag where you set it and then read it to see what it is. It's an interesting little way of using it. Let's go down now. We've got this other circuit here, which is an internal pull-up resistor. Here I talk about this pin and port. So when I'm talking about a port as small letters, or port with capital letters, or pin with capital letters, this explains that. Now what I want to do is have a look at the pull-up resistor. So we don't have to have a pull-up resistor with connected to our switch. We can just have the switch here, and we can turn on this. Now this gets a little bit more complex in terms of the logic, so we'll just zoom in just a little bit on this. So this transistor here, normally you apply a 1 or a high to turn on the transistor, but this has got a little bubble on the front of it, and you can see that bubble means that a low will turn it on. And of course this is an inverter, which means a 1 will turn this on. And an AND gate, to get a 1 on the output, means that all of the inputs must be 1. So here's how we get a 1 on our on this to configure on this transistor to turn on the pull-up resistor. The first thing is the pin must be configured as an input. Of course, if it's configured as an input, this is low, which means that the tap is turned off, the buffer is high impedance, and that low goes through here to this bubble, which means that it becomes a 1 on the input of the AND gate. This is driven, we have to actually drive the port register to 1 to turn on the internal pull-up resistor. And I'll just show you that in the code. Where's my, let's just find that. I've disappeared it. Let's bring this back and have a look at this. And you will find that this line here activates the internal pull-up resistor. So we look like we're driving the output. Well, actually, that's the register we're driving, but we're not actually driving the output as such. We're just driving this register to make sure it's a 1, so the 1 comes through and activates this AND gate. The other activation for this AND gate is PUD, which is the pull-up disable. So we can actually disable all the pull-up resistors in the microcontroller if we want to, just by setting that bit in one of the registers, and you can find that PUD, pull-up resistor disable, in one of the registers in the microcontroller. So if that's low, and that's high, then we will activate the pull-up resistor. So that's how that works. So this is, as you can see, it's an interesting little example to understand what is happening between the hardware and the software inside a microcontroller. And just keep in mind that RTL perspective of what you've got is a huge amount of data path, which is registers and buses and counters and all sorts of things, and a control unit which is activating all of these control signals. As an exercise, what you could do is you could have a look at the data sheet and go to, and I'm saying here, go to section 14.3 on page 89. So let's go to 14.3, 14.2. That's the general one that we've discussed. and 14.3 on page 89 is here. Now you'll see that each one of the pins of our microcontroller has alternative functions, and you can actually see that this gives you a bit more insight into how those alternative functions are enabled. Yeah. Also, a really interesting aspect of this is this sleep. When this is configured as an input, and I'll go back to the input one. At the moment, when it's configured as an input, the potential here, whether it's high or low, goes all the way through to this synchronizer, which is really just 2 latches. Now, if we want to put our microcontroller into sleep mode, so it's reducing the amount of power it's using, the way we do that is we want to turn off all circuits which are being clocked so that they're not clocking. And the reason we do that is because when a circuit clocks, it uses power, more power than it does in its stable state. So what we have here is the ability to put it into sleep mode. What we do is we use this inverter here to deactivate this sort of, well, it's like almost like a little multiplexer, but it's only got one input and one output. And that pin there is also used to power up this transistor, which clamps this input to 0, which means then that there's no possibility of any changes on the input pin making it through the to the synchronizer and using power. An interesting little application of some switching and logic here to reduce power of that. Okay, so this is where I'm going to stop this, and then we'll look forward to the next video. Cheers.